Good afternoon, everyone. Introduce myself. I'm Martin Denault. I'm the technical liaison at ESAB Welding. Um, and today we'll be talking about the AWS classification system that is used in the A5 specifications that are then used to classify and approve your filler metals. These specifications are very similar between product forms and alloys and different types of materials. So they do get a little bit repetitive. So in this presentation, I'll be covering uh, the main types, whether that be shielded metal arc welding, gas metal arc welding, gas tungsten arc welding, etc., for carbon steel, and then I'll be covering some of the stainless and aluminum as well. But this could be what you learn here can be extended over to any of the specifications, whether that be nickel or copper, etc. I have this broken up by AWS specification, and I'll be jumping through different presentations for each one, and that'll give me a chance. If you guys have any questions, feel free to type them in the chat, and I'll be able to see those as we get through each specification and address your questions for that specification at that time, or if you don't get a chance to type it in there and we get to it at the end, that's no problem as well. So the first specification that we're going to be talking about is A51, and along with that, because of the close similarity, we'll talk about A55. These are both shielded metal arc welding specifications, so stick welding for carbon steel, as well as low alloy steel. So when a manufacturer attaches the classification to a product, for example, when you see E7018 on a product, that is the manufacturer certifying that that product meets the AWS specification. So you can ask for additional testing. That's always very common, or particular lot classes or different schedules of testing. But if you see that designation on a package, that manufacturer is certifying the product in that manner. AWS is not like some of the other third-party organizations where they do different levels of testing. It's more of a self-certification when you use that AWS classification. So we'll get into the A51 to begin with. So the electrodes in this specification are going to be classified according to the current, whether that's AC or DC, DC electropositive, DC electronegative, the type of coating that's on the electrode, the position that the electrode is able to be used in, and then finally the mechanical properties that are seen in the as-welded condition. So here are the main electrodes that you'll find in A51, the common ones being a 6010 or a 6011. Both of those are cellulosic electrodes. 6013 is also very common with high titanium and potassium. And then, of course, down a little further, the 7018, which is your low hydrogen potassium electrode. And you'll see in the next column over the welding position that these can be used in and the type of currents they're typically used with or classified with. So when we break down the naming convention, the E stands for electrode. The first two digits are your tensile strength. So in the case of a 6010, it would be 60 KSI minimum tensile strength, and then the yield strength that goes along with those. In the case of 7018M, where it's a military electrode, there is not a tensile strength that is specified in the standard, though there is a minimum yield strength for those electrodes. Then these electrodes may also have an impact requirement or a Sharpie test requirement. Again, we'll stick with like a 7018 that is going to, I'm sorry, 7018-1, that's going to require a minimum of 20 foot-pounds at -50 Fahrenheit. And for example, 6010, 6011, that's going to be 20 foot-pounds at -20 Fahrenheit. So these are, an impact test is where a notch is put into the sample block, and that is hit with a swinging hammer, and the amount of force taken to break that in foot-pounds is presented, and the sample is held at different temperatures depending on what's required by the specification. A55 is very similar to A51, just with different materials. The electrodes are still broken down by the current type, the covering, the welding position, but since these are low alloy products, the chemical composition of the weld metal is more tightly controlled. And then, of course, the mechanical properties that are yielded out of the weld metal. So just as with the carbon steel, the first digits, typically it's 2, but as we get into higher strength steels, it could be 3, are the minimum tensile strength that the material is capable of withstanding, and that's measured in KSI. So a 70 KSI rod would be 70, 100 KSI would be, that's where we get into 3 digits, would be 100, and 110 would be 110. The next 2 digits are the characteristics of the electrode. So just like in A51, an 18 would be a low hydrogen potassium electrode with iron powder, intended to be used in all positions with AC or DC electrode positive. To go, when this is where the point where A55 goes beyond A51, where we get into the additional designators on the end of the electrode designation. So the first characters after the dash will designate the deposited chemistry, whether or not it has passed impact testing requirements, and whether or not it's tested in the post-weld heat-treated condition. Typically in these specs where you see an L, that is designating a low carbon deposit, and in A55 it would be the last, the third designator in those supplementary places at the end. So when we have these additional designators at the end, there's some examples here to kind of break it into families of electrodes. So an A1 at the end of the designation would be a half moly or half molybdenum electrode. A B designator, and the X in this case could be filled in with a number of different numbers. For example, a B2, a B3, a B9. Those are all creep resistant electrodes. C is for nickel alloys, NM is nickel molybdenum, etc. You could see the different lists there. W would be weathering steels, and G, just as in all the specifications, is a general, or there's not specific requirements, or it's as agreed upon between the purchaser and the supplier. So if you see 2 different electrodes that have similar classifications and Gs, they are not necessarily the same product. That could differ between manufacturer. It could even differ within one manufacturer. It all depends on what the purchase agreement is and the whatever the weld engineer has specified needs to be met. Just some further designators here with examples of Sharpie V-notch impact testing requirements, or material that is tested after post-weld heat treatment. For example, a D2 designator is going to meet 20 foot-pounds at -60 Fahrenheit, and that will meet that after 1 hour at 1150 Fahrenheit. And you can see other examples there of the mechanical property requirements that are designated that are specified by those designations. Here's some just additional ones for the nickel. You'll see much lower impact test temperatures. Nickel improves the impact properties of these materials, so they're typically used at lower temperatures and thus are tested at lower temperatures. The creep-resistant electrodes, these are very common in the power generation industry, or where you see high temperature service, where these materials would be used in higher creep ranges. B2, B3 are probably the more common ones. And a few years back, we've gone away from the B9 or just B9, and now we're expanding into the B91. That would be the old B9 material, and B92 as we get into materials that can have better and better creep properties and can spend more time at these very high temperatures that they're seeing in those industries. Further examples, like the weathering steels, where you may have a component of copper or nickel or chromium to be more of like a maraging steel, where it's going to have some weather resistance. Are those W grades 1 and 2? And then finally, at the end of either the A51 or the A55 specification, you're going to have the optional supplemental designators. The most prevalent one is for hydrogen. All these would be considered low hydrogen rods. Most people are looking for H4 for one reason or another, but that is a maximum of 4 milliliters per 100 grams of weld metal, or 4 milliliters of hydrogen per 100 grams of weld metal that are diffused into that. And this is to minimize crack sensitivity, especially in the A55, where you're getting into low alloy, high strength materials. They are very sensitive to hydrogen embrittlement. So we typically make those type of electrodes either in H8 or an H4 to minimize that. And then the last designator there, the R, that is a moisture resistant designator. So those electrodes are tested after exposure to air. Typically it's 80 degrees Fahrenheit at 80% relative humidity, and that they are able to maintain that 4 milliliters of hydrogen per 100 grams of weld metal after that exposure. So you can be certain that those electrodes will maintain that low hydrogen designation if they sit out for a full shift. So here's a full example where we can break it down. So you have an E7018 H4R. The E stands for your electrode. The 70 stands for 70 KSI ultimate tensile strength. The 1 is an all position rod, so you can weld it flat, vertical, overhead, or horizontal. The 8 is your low hydrogen potassium and iron powder electrode, and it could run on either electrode positive or AC. It has a H4 designation, so it has the 4 milliliters of diffusible hydrogen or as a maximum. And then the R is your moisture resistance. Here's another example, 5. So we have a E8018, B6L, H4R. So again, E is going to be electrode. 80 is the 80 KSI. Same all position characteristic as in the last one, and the same low hydrogen potassium and iron powder as the last one. Now this is going to be a B6, so that's going to be a 5 chrome half moly electrode. And then the L, meaning low carbon in that deposit. The same H4, 4 milliliters of hydrogen maximum. And then the R for moisture resistance. So all of these electrodes that I showed can be broken down in this same way using the tables that are in this presentation, and all those tables are in those filler metal specifications to help you break down what that electrode is and what it's capable of doing. I'm just gonna check and see if there's any questions here, and if not, we'll move on to the next one. Let's see. Let's jump over to MIG and TIG. So this is again going to be for carbon steel. But this time we're going to be talking about gas metal arc welding or gas tungsten arc welding. So these are going to be solid or metal core wires. Same deal as with A51. By affixing these classifications to the product and the packaging and the certificate and the certs, the manufacturer is certifying that that product is meeting the AWS classification. It's not implying that there's any testing done on that particular lot. That would all come from A501, where you have your lot classification and testing requirements. So as I mentioned, A518 is for solid electrodes and metal core products. These are typically tested with CO2 shielding gas, and the metal core wires are tested with CO2 or 7525. So the difference with this specification is we're not going to just have an E, but we're going to have an R. So the E stood for electrode with the stick specifications. With these wire specs, though, we're going to be able to use them as rods for TIG welding. So the electrode, it's carrying the electrical current from welding. The R is not carrying electrical current, so it's going to be TIG welding, or in some of the filler metal specifications, it may be gas welding. But when there's an R, it means it's not carrying the current. The E is it's carrying the current. When you have both, it can be either way. So just as with the stick rods, the first 2 designators are going to be, or 3 are going to be your tensile strength in KSI. So ER70 is going to be a 70 KSI tensile strength product. The next designator, we commonly see an S for solid wire or in solid wire. And you're going to see the C if it's going to be a cord wire, a metal core product. And then the next digit for solid wire is going to be the nominal composition of the wire. The biggest effect that we see here is the silicon content, and also the amount of deoxidizers whether that be titanium or aluminum, zirconium, that we see there. And again, G is going to be as agreed upon between the purchaser and the supplier. So if you have an ER 80S-G, that you can't compare that to a different manufacturer's ER 80S-G without knowing what that agreed upon properties are. Whether that's a change in chemistry or it's additional impact requirements. So always be mindful when you see the G that it's not a direct crossover. You need to either have your own specification dictating what that is, or speak to the manufacturer with the requirements that you're trying to meet and come to an agreement of what's going to be supplied. With the cord wire, that next designator is also going to be the nominal chemistry requirements of that, as you can see here. And the last designator for the cord wire is going to be a C or an M. C being that the wire is intended for use with 100% CO2. Or an M that it was tested with mixed gas, so 75-25, so 75 argon, 25% CO2. And then just like stick electrodes, these products will often carry the supplemental hydrogen designator, so H16, H4, etc. Again, that's 4 milliliters of hydrogen per 100 grams of deposited weld metal. Solid wires are all typically H4 because there's nothing to carry the hydrogen. There's not a flux or anything that could carry the moisture, which would create the hydrogen. So though we typically see all solid wire as H4. So these products are tested with GMAW. They could also be tested as GTAW. If it's only listed as an R, that would be only intended for use as GTAW or TIG welding process. If you're going to have the ER, then it would be available for a gas metal arc welding or MIG welding process. We'll move over and we'll talk about low alloy solid wires as well here. So these are the same nomenclature as we saw in 518 for carbon steel. The solid wires are again going to be grouped by their chemical composition and their mechanical properties, and the same with the cord wire. So ER, electrode or rod, and then again we're going to have the tensile strength. Then we'll have whether it is a solid or a composite, so cord wire or solid wire. And then just as in A55, we would get into the alloy family. A being a molybdenum steel, B your creep resistant steels, Ni nickel addition for improved impact properties, W for weathering, and then G as we've talked about a couple of times. And just as in A55, there could be an L at the end designating a low carbon deposit. So here's some different examples that are broken out. So your molybdenum or manganese molybdenum products. You can see with, for example, the ER90SD2. So that's a 90 KSI tensile strength product, solid wire, and then it has that D2. So it's a manganese molybdenum wire, and it's it's able to meet a minimum of 20 foot-pounds at -20 degrees, and that's as welded, no post-weld heat treatment. Here's some of the creep resistant steels, some of the more common ones, and these are all going to be tested with a post-weld heat treatment. Here's those same creep resistant ones listed as cord wires. Again, note that they're all tested after a 1 hour post-weld heat treatment. And we have some of the higher strength steels out there, so 100 KSI plus. So these are all going to be high strength, low alloys, and tested in the as welded condition. On this next slide, these are nickel steel wires. So pay attention to the impact, the increased impact properties. So these are tested at, you can see here, -50, -80, -100. And if we go back one, we can see that these higher strength materials are only tested at -60. So, and there's minimal nickel in them. So we have much more nickel in these. Those were a little over 1%. And here we're looking at 1%, 2%, 3% nickel. And that is greatly improving the impact properties. So they're all showing a minimum of a minimum of 20 foot-pounds. But if you notice, the test temperature got colder, and steels go through a ductile to brittle transition temperature. So this is lowering that transition temperature, allowing the material to have a higher impact resistance at those lower temperatures. Here are some wires that are listed in AWS, but they're typically military wires. They're for welding on HY steels, so high strength steels for ship hulls. Weathering steels, we typically don't see these in solid wire. These are more of a cord wire product, and you'll see that it's alloyed with chrome and copper to give it that weathering characteristics. As I mentioned a couple times now, the G classification is all agreed upon between purchaser and supplier. So other than the minimum tensile strength that's shown in the classification, any impact requirements, any composition requirements are all on your own personal specification. So you can write your own specification, and we would produce the wire to meet those requirements. So again, be very careful when you see G that you make sure you're getting the product that you need. And as I mentioned before, hydrogen, you could tell it's starting to get repetitive with these specifications. They're all the same. So if you see H4, it's 4 milliliters of hydrogen per 100 grams of weld metal. These solid wire and cord wire are not going to have the R designator, but it will have those hydrogen designators. So up next, we'll talk about flux core wire. So this is going to be a mix of the solid wire and the covered electrodes. So we will have, we'll break it down in the same manner with mechanical properties, nominal chemical composition, positions of the wire, positions that the wire could be used in for welding. Then we'll also be mentioning shielding gas and the usability characteristics. So just like a stick electrode, E is going to be electrode. You're not going to use a flux core wire for TIG typically. There are some out there, but it's not that common. So all these wire products are going to have that E and not the R. They're all meant to carry electrical current. And then those first digits or the first digit is going to be your tensile strength. So 6 would be 60 ksi, 7 would be 70 ksi, 8 would be 80 ksi. The next digit is going to be the position. So unlike stick and solid wire, that the next 0 is not just part of the tensile strength. That is going to mean that it is for a flat or horizontal wire. 1 would be an all position wire. Then you're going to have a T because it is a tubular product, so a cord product. And then after that, you're going to have the next designator, 1 for multi-pass, 2 for single pass, and that's where you're going to have a lot of deoxidizers to deal with rust and mill scale. And then there's other designators. As you go higher, you're going to get typically better mechanical properties. For self-shielded wires, you're going to have other designators on there, whether they're for single or multi-pass, and then the weldability performance of the wire. So how is it penetration? Is it good for higher speeds? Is it good for thinner materials or root passes? Those designators will be after that dash. And then the usability designator, G, again, general classification. It's going to be as agreed upon. And then the last digit will be a C or an M. So C would be 100% CO2 wire. M would be for mixed gas. Typically, we see 75-25. So here are some examples. So the X means it could be replaced with different digits. So these are all E70 XT. So it could be a 7-0, meaning it's good for flat position, or it could be a 7-1, meaning it's good for all position. And then the rest of the digits just maintain the same. The nominal chemistry, or the maximum value for chemistry for these wires would all be the same, regardless of whether they are for flat or all position wires. And then the mechanical property requirements of the wires. So a 70 is going to be that 70 minimum, and some of them are going to have a maximum tensile strength or a minimum yield strength, as well as impact requirements, just like with some of the other products. For the chemical compositions of these, I just wanted to note that the T10, 13, and 14, they don't have chemical composition requirements. And we'll see, if you note the higher level of aluminum in these is permitted for that self-shielding characteristics, and that's because aluminum reacts with the nitrogen in the atmosphere to help prevent porosity. Supplemental designators, the J is showing that it has improved impact properties, and then a D is an older designator, but you'll see it fairly often, and that was that it met AWS D18 for seismic applications, and then hydrogen designators, just as we've been going through for the past few presentations. Now we're going to jump into some other products. So I'm going to touch just briefly on aluminum, because it's fairly common out there, but we have a whole presentation dedicated to aluminum, because it's to spend the time to go through the alloy families and the possible filler metals it takes a full hour by itself. So this is just going to be a very high level view of A510, where we just touch on the families. We won't get into the details of the subcategories in each of the families. So just like with solid wire, these are ER, so they could be electrodes or rod. Be used for either MIG welding or TIG welding. And the basic families are the 1000 series, so that's basically pure aluminum. 2000 is aluminum copper. 3000 has manganese alloyed in. 4000 would be silicon, and 5000 would be aluminum manganese. You can then break these down further by the remaining digits that are in there. But this aluminum, we do aluminum in a different presentation, so I just wanted to give the high level view here. The common electrodes we would see would be like a 4043, so that ER 4043, or another common would be ER 5556 or 5356, where you have magnesium alloyed in with the aluminum. Aluminum filler metal selection becomes very complicated, and we'll cover that in the aluminum slides. Okay. Now we'll jump into some stainless here as well, because I had saw some people were asking questions about that, so I want to make sure I cover that a little bit more in depth. So we'll start off with the shielded metal arc welding A54, so stick rods for stainless. These electrodes are classified by their chemical composition, as opposed to the carbon and low alloy products that were all categorized by their tensile strength as the primary factor. Stainless is not. Stainless is broken down by chemical composition, and mechanical properties of the weldment are a secondary consideration. In the solid wire spec, they're not even mandated, though if you meet the chemistry, you typically meet the mechanical properties. Corrosion resistance is not a factor that's considered in the AWS specs. That's something that needs to be it's outside of the scope of AWS and needs to be considered separately, either through different recommendations or corrosion testing. But typically we match the weld metal to at least be as corrosion resistant as the base metal. So you have to be careful with choosing your filler so you can maintain that corrosion resistance. So just like in A51, you're going to have an E, meaning this is an electrode, is meant to carry the current. And then you're going to have the next digits are going to be your grade of steel, and broken out by chemistry. So the example here would be E316. So that would be a 316 grade of steel. You could have a 317, a 347, etc. It just depends on the chemical composition that you're looking for. The next digits are going to be whether it is a low carbon, a high carbon, whether there's going to be additions of other elements in there. For example, you may have a 409 NB, where you have additions of niobium, or a 410 nickel moly would be another common one, where it's a 410 steel, but those additions of nickel and molybdenum. The last two digits are going to be your current position designator, or the type of electrode that it is. A 15 type is a basic electrode intended for DC current can be welded in all position. 16 and 17 are going to be very similar. They have slight differences, but they're both rutile electrodes. And then a 26 type is it's a steel core, not a stainless core, and you're getting all your alloying through the flux. Those are a lot less common, but they are less prone to overheating. So the 15 type coating has really poor weldability. There's a lot of spatter. Slag release is very difficult, but it has great mechanical properties, especially impact resistance. Your 16 is a rutile, but a basic rutile. It's probably the most common in North America, where a 17 type, an acid rutile, is a lot more common in Europe. Both have very good performance and good slag release, and we're seeing that historical divide of in North America and Europe kind of phasing away. A lot of people in North America are moving towards the 17 type, and as it has a little bit better weld appearance. So here's an example, 308L-15. So it's an electrode. It has the composition of a 308, so used to weld a 304. It's an L, so low carbon deposit, and it's a 15 type, meaning that basic electrode, and it can be used in all positions. Here's another example of 309 LMO-16. So it's a 309. The intent is to weld on 309 steels or a dissimilar joint between carbon and stainless. So E electrode, 309, your chemical composition, low carbon, additions of molybdenum, and a 16 type. So it's your rutile electrode. Finally, we're going to go through solid wire stainless here. So again, just like with stick rods, we are going to be basing these off of chemical compositions. And there are not going to be any tensile strength requirements in this specification. It is purely chemical composition. The other product that is covered in 5.9 is strip electrodes. So that would be used for sub-arc welding strip or electroslag strip. This is a lot less common, so I just give a little bit further explanation. So these are strips that are typically 30, 60, 90 millimeter wide strip, and you're using it for a cladding operation in order to build up a surfacing on another plate to provide corrosion resistance, not for sub-arc joining application. So if you have a pressure vessel that needs to be 2 inches thick for strength, but you don't want to make the whole thing out of stainless because that would be expensive, you can clad the carbon 2 inches of carbon steel with a stainless, and then you could have the corrosion resistant properties of the stainless, and then you can get all your strength from the carbon steel and not have to make the whole thing out of stainless. E would be electrode. Then you're going to have a R for wires or rods, so not current and non-current carrying. C would be for a cord wire product, and then you typically see EQ for strip. The next digits are going to be your chemical composition. Again, same example as last one, 316, and then your next alpha characters are going to be for the supplemental designators of low or high carbon. Is there additions of silicon? We typically see that with for the gas metal arc welding process. Higher silicon additions are going to improve the wetting characteristics, so that affects mostly weldability. Doesn't really affect corrosion resistance. And then additions of other elements, whether that be molybdenum or niobium, manganese, etc. So when it comes to the solid wire, these can often be dual classified. So a product could meet a 308 or a 308L. So it can meet the standard grade, or it can meet the low carbon. And so we'll use that as an example here. So ER 308L, it's an electrode. R, it's a rod. 308 chemical composition, so nominally a 19.9 or 18.8 chemical composition. L, so it's a low carbon deposit. And we can use a 400 series as another example. So it's an electrode, it's a composite wire, so a cord wire. It's a 439 stainless composition with additions of niobium. So that's how you break down these different filler metals, and then all of the grades are then listed in the relevant AWS specification. I have some questions that were written ahead of time. So the first question we have is in general, filler metal has recommendations for choosing shielding gas. What happens if one successfully tries to approve WPQR for use with a different shielding gas? So the shielding gases that are used in the AWS specifications are for classification purposes. That's not to say you could use a different shielding gas. For example, people will use, instead of using 75-25, they'll use an 80-20 gas, because in certain parts of the world that's more available than 75-25, which we commonly see in North America. With for example, stainless MIG welding, you may see, or aluminum MIG welding, you may see additions of helium to provide better wetting characteristics and better heat transfer across the arc. So the gases listed in the AWS specification don't really have any bearing on what you qualify for your WPS. They're just there for classification purposes. The next question we have is compatibility on the stress tension between the two materials. Okay, so I think you're asking about if you have two dissimilar materials. So let's say you have a low alloy, or I'm sorry, a carbon steel like A36 or 516 grade 70, and you're trying to weld that to low alloy, high strength. In that case, you typically defer to meeting the properties of the lower tensile strength material. So in that case, if you're welding a 36 yield material to a 100 KSI ultimate tensile strength material, you would use a 70 KSI rod to meet the requirements of the lower of the two tensile strength materials. That's what you typically do. When it comes to aluminum, again, there's a lot more considerations there. Are the base metals even compatible, or is there other considerations like a color match, or for anodizing, or are you is it being used in high temperature service? So that's with aluminum, we would need more details. For stainless, again, you're matching the corrosion properties of the lower of the two materials, because the lower of the two is going to be your weak link. So there's no sense in putting higher strength or higher corrosion resistance weld metal in. It's unnecessary and could cause additional problems such as cracking issues in high strength material or galvanic corrosion issues in a stainless. Next question, can I find a list or table of the most commonly used electrode for different applications? There's so many different applications out there with different base metals. I don't know of a table like that, other than in the back of the D1 structural steel books. There are a lot of recommendations in there, especially with the pre-qualified joints. That's kind of where I would point you to find a recommendation table. When it comes to aluminum, then there is a joining chart for selecting filler metal, as well as stainless. There are joining charts for choosing dissimilar base metals and what stainless filler you use. For carbon steel, I don't know of a table like you're looking for. So somebody said, how to choose the right type of metal filler for steel. You primarily are matching the properties of the base metal. So you're meeting the minimum tensile yield, and then you're meeting any impact requirements that are necessary for the design. What key information should be reviewed on a filler metal specification sheet before selecting it for a welding procedure? How do filler metal specifications influence the mechanical properties and performance of the final weld? Okay, so if you're looking for what should be reviewed for a filler specification, I would refer to AWS 5.01. That is the welding and brazing consumable specification for procurement. That is going to lay out the lot classification, the level of testing that you could that are commonly specified, and there's some kind of suggested forms in the back where you could fill it out to make it very clear to the supplier what you're looking for. You list the specification, the classification you want, the dimensions of the product, the way you want it packaged, whether it's in a spool, a drum, a can, a bucket, whether you want it in vacuum packaged or hermetically sealed container, and then the lot classification, level of testing, additional requirements. But those sheets in the back of 5.01 are going to be very helpful for you in that case. And then to answer your second question, how do the filler metal specifications influence the mechanical properties? They set a minimum. So by putting that AWS classification on the product, the manufacturer is certifying that it is meeting those minimums. So if you're looking for an 80 KSI minimum tensile strength, don't use a 70 KSI product. You have to know what your minimum is, and then you can choose from there. But it's giving you a minimum. So if you're looking for above and beyond, if you're looking for a minimum of 87 KSI, don't pick the 80 KSI rod and hope that it'll meet it. It might, but it might not. So you might want to defer to the next one up and go to a 90 KSI, or if you're buying enough and it can dictate a manufacturer making a special run for you, then you can go to a G classification and specify that 87 KSI that you want, and it, come to an agreement with a manufacturer to produce it. Let's see. I would like to know how to identify different types of metal. That I would say the density or a PMI gun is going to be your friend there. I mean, there's a lot of other ways to identify metal, but a PMI gun is going to be probably the most accurate for what we need for selecting a filler metal. What are the most common misinterpretations of AWS classification, and how can they be avoided? I would say probably the most common is when someone says, I need low hydrogen, and they say they can't accept anything other than H4. I'd say that's the biggest misconception, that an H16 is technically low hydrogen. So is an H8. I mean, it really depends on what you're doing. But I just see a lot of people deferring to H4 when they may not need it, but they see it as the best, and they immediately go for it, and they're paying a lot more for a product than they need to. This person had a lot of questions. Next was, how do environmental factors, temperature, corrosion, influence filler metal selection based on AWS classification? So for temperature, then we would be looking for impact resistance. So if you're building something for, if you're very far to the north or south and have very cold temperatures, you may be looking for better impact properties, because the the structure you're building may see negative 40 degrees. So you're going to want something that's capable of withstanding the loads at those temperatures. So those supplemental designators are going to be key for that. As far as corrosion, that's not a consideration in the AWS specifications or in the codes. So like D16 for structural stainless corrosion is not a consideration. You need to use other standards and other types of testing or material selection in order to choose for corrosion resistance. I mean, there are some very general considerations out there, and there's a lot of corrosion handbooks that are freely available out there that give very broad recommendations for different environments that are typically seen. Okay, how does ESAB ensure compatibility between its specialty alloys and AWS classified filler metals? So if we are listing an AWS classification on a filler metal, that is us confirming that we have met the requirements of that specification. So and that those are a minimum, and then we are testing the product to confirm that it is meeting it. Let's see. Okay, beyond matching basic tensile strength and position, what are some of the most critical optional designators? Hydrogen, impact toughness, special chemistry that welders can often overlook, and provide examples of how difference could drastically affect a specific. Okay, so I would say beyond matching the strength, someone is going to be choosing that filler metal, and they're going to specify it. If it's not specified, I would say that the engineer of record needs to be approving what filler metals are chosen, because just because you're fabricating it doesn't mean you know what the intended design or end use is. So hydrogen designators, I mean, that's an easy enough choice. If you're welding that with a material that's susceptible to hydrogen cracking, you may want to add that on. But impact toughness, that's going to be what was designed for. I hope that answers your question. If not, please feel free to message me, and we could talk more about it, either here or offline. Okay. I'm not sure what some of these are. When you okay. Right. How close does the metal need to be to the filler metal? So typically we want to meet the minimum properties of the base metal. So if you have a 70 KSI minimum for your base metal, you would want to use a 70 KSI minimum filler metal. They're both likely to be over that minimum. Steel production has improved drastically over the years. So when something is a 70 minimum, it's probably in the 80s, unless there's a yield maximum on it. But we're getting very good properties out of steel mills these days, and I would say the same would be said for filler metals. Melts of steel are much cleaner than they used to be, but if the product is being designed for its minimum, that's what you use for your design. So there's not really a point in going higher unless you're trying to have a reduced factor of safety and really push the design limits and reduce weight. Then you may test particular heats or lots, but normally we're just trying to match that minimum. So I would say if your product is 75 KSI minimum, I would defer to an 80 KSI filler metal. I hope that's what you're asking in that question. Okay, and that was all the questions we had ahead of time. Do we have any last minute ones in here? Okay, yeah, we do. All right. Let me go back to the beginning here. Regarding the shielding gas question, it's important to emphasize that shielding gas is not only influences the mode of metal transfer during welding, but also significantly affects the weld metal chemistry, for example, altering the percentage of argon and gas mixture. Composite. So yeah, so I mean, like I said, with the shielding gases, the shielding gas that's listed in the A5 spec is just the shielding gas that is used for classification. That's not to say you can't use other ones, and there are shielding gases which you may want to avoid in certain certain applications, but your WPS and PQR are going to be what show that your combination is working, and these specifications don't have anything to do with the WPS. So these are just for filler metal classification. But yeah, like you said, certain gases could adversely affect weld metal deposits or be beneficial in others. For example, hydrogen might be great to use in a shielding gas for stainless, where it's not susceptible to hydrogen cracking, but could be extremely detrimental with a low alloy steel, where you're trying to minimize the amount of hydrogen that is in the weld. Okay. The filler metal data book would be available online, or Melissa, I don't know if you're able to send that out. Filler metal has some classifications, for example, TUV approval, which states gas should be M21, can use a different shielding gas resulting in reduction. So yeah, so if you're dealing with third party approval like TUV, and when it's a pressure device that is being constructed under TUV rules, that's totally different. You're gonna have to have a filler metal that was approved by TUV and that is meeting the correct specification. So yeah, the TUV may audit us as a manufacturer and review our testing of the product, even down to a particular heat or lot, and sign off that they've witnessed that testing and that it's in compliance. Well, thank you all. Sorry we ran a little bit over time here. I hope you guys all found this informative.